In the last video, we introduced indifference curves and discussed how an indifference curve is a line for which every point on the line represents a bundle of goods, and every bundle of goods on the line would give the same utility. So for example, each bundle on this curve might give a utility of 4. Moving on from that idea is the fact that every graph of utility will have an infinite number of indifference curves. Because if this is an indifference curve that gives a utility of 4, there's some indifference curve above it that gives a higher utility of 4.2. And there's one above that that might give a utility of 5. And there's an infinite number of them in the space in between. And so these indifference curves, while we don't usually draw them all, really fill the space of the graph. And indifference curves follow a few rules. The first of these rules is the one we talked about, that every point on the indifference curve gives the same utility. The second is that the curves can never cross. And it's easy to see that this is the case if we draw a graph. And let's say, for example, that we had two indifference curves and we let them cross. Let's show that this can't be true. Let's take a point here, call that point A, call this point B, and call this point C. So going by our rules that all points on one curve have the same utility, and that curves that are farther out have more utility, we would know that C and B must give the same utility. So C is equal to B, because they're on the same curve. We also see that A and B are on the same curve, so A must have the same utility as B. And we can easily see that A is on a curve that's farther out than the curve that C is on. So A must be greater than C. But we have a problem here, because now we've shown that A is equal to B is equal to C, and we've shown that A is greater than C. This is a contradiction, so they can't all be true at the same time. And that proves that indifference curves can never cross. There are an infinite number of them that fill the space, but they each are on their own distinct line. Another thing that we mentioned in the previous video was that the shape of an indifference curve is affected by what the utility function is. So a utility function of xy will have a slightly different set of indifference curves than the utility function that is xy squared. So now we're going to take a minute and just go over a few basic utility functions and what their indifference curves look like. So we already went over the utility function xy and showed that the indifference curves have this general U shape that goes off into infinity in both directions, but never really touches this line, just asymptotes towards it. Another common utility function is the utility function for perfect substitutes, something along the forms of x plus y, and the indifference curves for that are linear. There are an infinite number of linear curves. Additionally, the utility function for perfect complements would look something like this. It uses a min function of x and y, and those indifference curves actually have a corner. You have an infinite number of indifference curves that look something like that go off to infinity. Another example, we could have something like x squared plus y squared, and in this case you would actually get indifference curves that curve the other way. These are just a few examples, and we'll go over them in much more detail in later videos, explaining why they are the way they are and how we can work